Welcome to Lecture 2 in our Unit 6.5 Covalent Bonding Extension and Intermolecular Forces. So today we're largely focusing on the CH bond within molecules, and we're going to start with the smallest molecule that consists of CH bonds, and it is methane. So let me just get a pen out here. All right, we've seen that a lot in class, and we've determined that the molecule itself is nonpolar, so it doesn't like to attract its neighbors. So the sample has a tendency to stay gas. You have to get it very, very cold before methane will form a liquid and then a solid. So with all reasonable temperatures that we would encounter, methane is a gas. Methane is a non-polar molecule. Now, we've defended that largely in class based on the symmetry of the bonding. Now, it has what's called a rotational symmetry. So I could turn that molecule and keep rotating it in different positions and bring a different H atom up to the top, so to speak, and the molecule would map on top of itself. So we've always argued for its non-polarity based just on this rotational symmetry of the molecule. And that's true, but there's another reason that is more important and relevant to this particular lecture, and that is in the nature of the carbon-hydrogen bond itself. So we've been getting familiar with the electronegativity chart, where we look up the two atoms on either side of a bond, and the one that's got the bigger number on the electronegativity chart holds the shared electrons a little bit more, and therefore gets a delta minus. And we can play that game with the carbon-hydrogen bond as well. So we look up carbon in the electronegativity chart. We look up hydrogen in the electronegativity chart. Carbon has an electronegativity of 2.55, and hydrogen, when we look that up in the electronegativity chart, we'll have an electronegativity value of 2.2. So then we take the difference between those. That's how we learn where to put the delta plus and where to put the delta minus. And so we get 0.35, and that is a small enough value, and there are other particular things happening in the CH bond which have allowed chemists to determine that the CH bond is essentially nonpolar. So even though it has some electronegativity difference, it's small enough, and through experimentation, chemists have determined that more or less the CH bond is a nonpolar bond. So that makes the particular geometry of the molecule, or as we will see, the part of the molecule, makes the particular geometry of it less essential, just seeing that it's composed of CH bonds. Okay, so now we're going to start to look at molecules that have other parts to them, so we can break the molecule down into parts. And we're looking for a portion that is made of just CH bonds. And so here in question number 1, we have an ethanol molecule, and this was one of the liquids that we were using in the penny lab. We were dropping drops on top of a penny to see how large a bubble we could get on top of the penny before the liquid overflowed. And so what we want to do is we want to justify, or we want to analyze how well ethanol will attract its neighbors. And we do so, it looks like it's asking for 2 parts here. Use an electronegativity chart to label the delta plus and delta minus, I'm just reading this right here, for the OH group. Okay, so the CH part of the molecule will be its own thing, and then the OH will fit into what we've been practicing, where we look for the O and we look for the H in the electronegativity chart. And when we do that, so when we analyze the OH part, we see that oxygen has a higher electronegativity value in the electronegativity chart. And therefore, between the oxygen and the oxygen gets a delta minus and the hydrogen gets a delta plus. Now, looking at the rest of the molecule, it's just composed of CH bonds. So I can take a look at this whole thing and say, well, this is essentially nonpolar. I don't have to look at the electronegativity chart. I don't have to look at the particular structural geometry of the molecule. I just see that it's made of just C's and H's, and I can say essentially nonpolar. Okay, to the next page. Acetone was also used in the Penny Lab, and here it's the same analysis, right? So we're looking at parts of the molecule that are just made of CH bonds, and we're going to conclude that that is essentially nonpolar, and then we're going to focus in on another part of the molecule that has different atoms, and therefore we will do our more well-practiced skill of looking up the atoms in the electronegativity chart to see which gets the delta plus and gets the delta minus. So here I'm drawn to this part of the molecule, which is essentially nonpolar, and this part of the molecule that's essentially nonpolar because they're made just of CH bonds. So let me write essentially nonpolar in for those. And I've still got a remaining portion of the molecule. So I'm going to look up C and O in the electronegativity chart. The one that has the bigger number is going to be more negative in that covalent bond. So oxygen is more electronegative, so that becomes the delta minus. Carbon becomes the delta plus here. So this is a molecule that has a portion with some separation of charge. This will allow it to attract its neighbors some, but it's also got large portions of non-polarity, which means that's a part of the molecule that won't attract its neighbors. And so what we're doing during the Penny Lab is we're comparing molecules to see, gosh, which ones have the greatest ability to attract their neighbors. And lastly, we have diethyl ketone. That is not a molecule that we'll be using, but it's got the similar look to it in that there are parts of the molecule that are essentially nonpolar because they're made of just CH bonds, and a part of the molecule that does have some charge separation. So it will have a delta plus and delta minus, and that part of the molecule will be able to attract the same delta plus delta minus part of the neighboring molecule. Okay, so this same molecule has been offered for us two different ways. One is the ball and stick model on the left, and the other is the more traditional, what we've seen, the chemical formula, but it's the same molecule. So gosh, let's start with the traditional here. So looking at that, I'm looking for parts of the molecule that are non-polar and parts of the molecule for which I'm going to do my electronegativity chart analysis on. And so I see two large groups of this molecule that is just made of C's and H's. I see one here, and I see one here. And these parts of the molecule are essentially nonpolar, so I'll write that in. And same thing here. I guess I'll just draw arrows there. Okay. Then we have a part of the molecule, namely the C and the O, which is not composed of CH. So therefore, we're going to do our more traditional and practiced analysis of looking up these atoms on the electronegativity chart. When we do that, we see that oxygen has a higher value. So oxygen will get a delta minus, a partial negative charge in that sharing of electrons, and the carbon will have the partial positive charge. So in this molecule, it has much larger portions of nonpolarity. So it's going to be harder to attract its neighbors because more of the molecule is essentially nonpolar. Yes, it has a small portion that's got separation of charge, and it's that separation of charge that can attract its neighbors. So we're looking at relative amounts of nonpolarity to polarity in the molecule to make an educated guess as to how well it attracts its neighbors and therefore how large a bubble it will make on the penny. So applying only the skill that we have learned in this particular lecture, we compare diethyl ketone in its rather large regions of nonpolarity to the acetone, which has smaller portions of nonpolarity. So relatively speaking, this acetone can attract its neighbors, has greater attraction for its neighbors than the diethyl ketone. Just look at the structural similarity between those with the CO double bond in the middle, and then we've got these chains of non-polarity on either side. Diethyl ketone has larger chains, therefore, based on what we've learned here, we'll would conclude that it wouldn't attract its neighbors as well, so it wouldn't be able to make as large a bubble. Okay, so I'm going to just check this because I'm over 10 minutes here, and I have to keep these videos around 10 minutes. So our well-practiced skill here would be to look at this molecule, identify portions of the octanol molecule as polar or nonpolar, and we have a huge portion of it that's essentially nonpolar, and we'll stick with the red pen. It's got the delta minus and delta plus already done for us here. This is the part that is polar on that molecule. Okay, thank you.